So, you're standing in a lab looking at a drawer full of SEC columns and wondering, which one of these should I actually use? It's honestly the very first and most important question we have to answer whenever we start developing a new method. Choosing the wrong column can waste days of work. So think of this video as your practical SEC column selection guide. We're going to break down the chemistry and the math so you can pick the right tool for the job every single time. Before we talk about picking a column, let's remember what we are actually doing. In SEC, we aren't using chemistry to make molecules stick. It's actually the opposite. The column is packed with beads full of tiny pores. The big stuff, aggregates, can't fit inside, so they shortcut around the beads and finish first. Your main stuff, monomers, are smaller, so they wander through the pores, which slows them down. Finally, the smallest pieces fits into every single tiny pore, getting delayed the most and coming out last. If those tunnels aren't the right size, everyone takes the same path, and you get no separation at all. Now that we know how the tunnels work, how do we actually pick the right column? This is the most critical part of your method. Think of this as your 4-step checklist for building a separation system, starting with choosing the right resin and sizing your pores to catch the right molecules. Next, you tune the system's flow and dimensions like a radio dial to keep everything moving smoothly. Finally, you add a protective layer to shield your expensive gear from getting trashed by pressure or debris. So, the very first step is picking your resin, which usually comes down to a choice between the high precision of silica or the rugged durability of polymers. Silica is a high-performance option for proteins and antibodies because it's super rigid and gives you really sharp, high-resolution peaks. The downside is that silica is a bit picky. It can dissolve if the pH gets too high, and your samples might stick to it unless the surface is properly coated. On the other hand, polymer resins are the rugged workhorses. They're great for synthetic polymers or nucleic acids because they can handle a huge pH range in tough organic solvents without breaking down. They aren't quite as stiff as silica, though, so you have to be careful not to crush them with high flow rates. Basically, use silica when you need precision for biologics, and go with polymer when you need a robust material that can survive harsh chemical conditions. Step 2 is a make-or-break metric, picking the right pore size. Think of these beads like a filter. If the pores are too small, your molecules just wash right past without being separated at all. If they're too big, everything gets lost inside. Your prime objective is to find that Goldilocks zone where your target molecules can move in and out of the beads freely without getting completely excluded or permanently stuck. To get the math right for this maze, we use 2 simple rules of thumb. First, always pick a pore size that's at least 2 to 3 times larger than the diameter of your biggest target molecule. This gives them enough room to actually enter the bead. Second, for the best possible resolution, aim for your molecule's weight to land right in the middle of the column's fractionation range. Doing this ensures your small fragments and monomers can fully explore the pores while keeping large, unwanted aggregates out, which maximizes your separation time and gives you much cleaner data. Think of this as your cheat sheet for matching pore size to your molecule. It's like a ladder. At the bottom, you use small 100 to 150 angstrom pores for peptides to get the best resolution. Moving up, the 200 to 300 range is the industry standard for antibodies, which is perfect for separating single monomers from those larger clumps or dimers. For the really big stuff, like ADCs, large complexes, or even viruses, you have to jump up to 500 or 1,000 angstroms. If those pores aren't big enough, those massive molecules will just bounce off the beads and wash out immediately without any separation at all. Now that our resin and pores are locked in, step 3 is all about tuning the hardware. We're basically balancing 3 main things: the length of the column, its diameter, and the flow rate. Think of this slide as your trade-off dashboard. In SEC, you can't have everything. If you turn one dial up, something else usually has to give. First, there's column length. A longer column gives you better resolution because the molecules have more time to separate, but the trade-off is a much longer run time and higher back pressure. Next, we have column diameter. Moving to a narrower column improves your sensitivity and keeps your sample from getting too diluted, which is vital when you're working with low-concentration biopharma samples. Finally, there's flow rate. While it's tempting to speed things up, going too fast actually kills your resolution. If the liquid is moving too quickly, the smaller molecules don't have enough time to actually diffuse into the pores, and you lose your separation entirely. Finally, Step 4 is all about protecting your hardware. These SEC columns are expensive, high-value assets. If you treat them right with regular maintenance and proper protection, a single column is engineered to last for 500 to 1,000 injections. However, if you ignore things like pressure limits or let debris into the system, you'll trash your column long before that. To hit that 500 injection mark, you need to follow this longevity checklist. First, filtration is non-negotiable. Always centrifuge your samples and filter your mobile phases through a filter to catch clogs before they start. Second, use a guard column if you analyze a lot of dirty samples. It's a cheap, sacrificial piece of hardware that traps gunk, so your expensive analytical column doesn't have to. Third, watch your pressure. Avoid shocking the system with sudden flow increases, and keep an eye on high back pressure, which is the first sign your column is fouling. Finally, don't store it in salt. High salt buffers will ruin your resin over time, so always flush the system with something like 20% ethanol to prevent bacterial growth while it's sitting on the shelf. Treat the column well, and it'll last you a long time. To wrap everything up, here is your benchtop cheat sheet to mastering the SEC maze. First, choose your base material. Use silica for protein work or polymer for synthetics and harsh pH. Second, size your pores to be 2 to 3 times larger than your biggest molecule. Third, dial in your dimensions. Stick to a 300 millimeters length for the best resolution and a narrow diameter for higher sensitivity. Finally, protect your investment. Centrifuge samples, filter mobile phase, use a guard column, avoid sudden pressure shocks, and always store in 20% ethanol. If you follow these 4 steps, you'll not only protect your hardware, but ensure your data is as clean and reliable as possible. Master the physical maze, and you master the method.